Really? Yes. So the Copernicus program was established in order to provide objective information about the environment, to make it easy to work with Earth observation data, to make the data free, to make it accessible, to make it quantitative, and to sort of set up a system of services and data sets that are complementary to each other so that there are not that many gaps or blank spots in our understanding of the Earth system. So actually, I think it's a really inspiring concept to invest public money in a global scale Earth observation approach. And this is what the Copernicus program was designed for. So this includes, of course, not just the environment, but also energy, civil protection, security, humanitarian aid. And back when this idea was formed in the early 2010s, I think they really anticipated something like what we have now. Maybe they didn't even expect it to reach this scope. The nice thing with the Copernicus program is that it's a long-term commitment. So again, if you want to build a public service on Earth observation, or if you want to build your business on Earth observation, you have to be absolutely sure that the data is going to be there in 5 years, in 10 years, hopefully also in 20 or 30 years. And luckily, we have this collaboration of countries within the European Commission who actually committed to sustaining this fleet of satellites. And that means sending up a satellite when one of the old ones is broken. And I have to say, we are in a very tight spot with that, because with the changed situation with Russia, we can't rely on their launch capacity. So we have a big backlog. We hope to launch Sentinel 1C on the 3rd of December. That's going to be our next satellite. But that satellite has been waiting for a long time for the appropriate launch capacity. But even though it's going to be more expensive and more difficult, since we have this commitment, the satellite is going to be launched. So they're actually doing what they say. But this is not only about satellites. There's also a lot of work invested in the ground infrastructure. And this includes the satellite receiving stations, of course, the servers where the data is hosted, the infrastructure and the software environment for reaching the data. And this is what CDSE, Copernicus Data Space Ecosystem, is about. And also a network of ground reference data sets and stations wherever appropriate. And in addition to the satellites and to the raw data sets, there's also this network of Copernicus services, and you're going to hear a lot about them: atmosphere, marine, land, climate change, security, and emergency services. So what the Commission is trying to do is to process the data and create data products that are actually relevant directly for policymakers at every level. This includes your village or your local council, but also, of course, countries and international institutions. They are trying to pre-process the data to make it easy to say per microphone. So where did the Copernicus program start? Europe was actually always relatively successful in Earth observation science, but this relied heavily first on the MODIS program, which was launched and maintained by NASA. Again, the data were shared freely, actually in a special way. They were directly broadcasted by the satellite, and if you had the right kind of radio antenna and dish, you could just listen to the data when the satellite passed over you. And that allowed many countries to set up their own MODIS receivers and to download data from their own territory, because as long as the satellite was in the line of sight, you could directly take the image that it was seeing. So MODIS satellite mosaics of Hungary were processed like this in the early 2000s, and there was a lot of science invested into this. But you know how science projects go. At some point, you run out of funding, and then you struggle to maintain it, and it's never going to turn into a real service. Then again, in the early 2010s, the MVSat program was launched, and it was a massive program. It was a satellite which was the size of your regular city bus. It carried many different Earth observation systems on one single platform. The data was also relatively easy to access. I mean, it was free, but the infrastructure was, of course, a bit clunky. But again, the water quality or soil moisture or land cover services or studies that were built on top of this were not really easy to turn into services. And so the idea came to establish what we need for our long-term global Earth observation service. And GMES, as it was called back then, Global Monitoring for Environment and Security, aimed to be this completely comprehensive overview of the global ecosystem. And the global ecosystem, of course, includes people. So it was designed from the ground up to serve free and open data. And this was very much based on the success of the MODIS program and also the Landsat program. Landsat was first designed to be a a market-based thing, just like Planet or Airbus satellites operate today. But then after a while, the decision came to publish the archive and also to make the data free and open. And that's actually the big start of public environmental Earth observation. So the success of the Landsat program and the public release of the Landsat program was one of the reasons why the Copernicus program was launched. What you see here is actually an ENVISAT MERIS-based study. Just take a look at the pixel sizes and the detail and the resolution. This was calculated from a time series of ENVISAT MERIS water quality data on Lake Balaton by Polybov and Sentinel Palmer, who compared different water quality algorithms to actually select the right one. So this is what MERIS could do. The start of Copernicus, or the birth of Copernicus, can be traced back to 1998 in what is called the Baveno Manifesto. Baveno is a small city in northern Italy on the shore of Lake, I think it's Lake Garda here. And there, a group of scientists made a strong statement that this is going to be needed for the future. And it took a long time until the first satellite was launched. Of course, it was several decades. But this manifesto was really well received by the European Commission, and they made a commitment to establishing the European capacity for monitoring. They established the GMES Bureau in 2006. And actually, it's nice because they didn't start with satellites. They started with the services. So the first task of the GMES Bureau was to establish services based on existing satellite infrastructure for the most important topics that they found the most pressing at the time. And then the Commission committed to the first Copernicus budget, which was 5.5 billion euros, and Sentinel 1A was launched in 2014. And then the last of the series, in a way, the Sentinel 6 Michael Freilich was launched in 2020. And now in 2021, another package of Copernicus budget was secured for the time period of 2021 to 2027. So again, we have a long-term commitment, and we hope that for the next EU budget cycle, there's going to be an ongoing budget again. And in 2023, Copernicus Data Space Ecosystem is launched, and I think that's really a revolution because the accessibility of the data is completely changed. And I hope to introduce you to this in a couple of minutes. Yes.
And billion of euros that integrate.
There has been a commitment in the budget to set aside this money, and then to split it up for different lumps depending on applications and years. But definitely this budget has been circled around that this is for Copernicus and not something else. Let's go through the satellite missions. Oh, an error. I'm talking about Sentinel-1, actually, not Sentinel-2. This is a synthetic aperture radar satellite. So it emits radio signals and it records them. What you see on this little drawing of the satellite is two things. One is that it has massive solar panels because it's generating the energy which it's actually sending down. And the other is the long antenna, the sideways facing antenna on the bottom of the satellite as it orbits. It's emitting this signal towards the side and recording the echo. And then it's resolving the distance across track based on the echo and the long track based on the time as it passes. A synthetic aperture is a complicated thing. The very basic law is that the larger the antenna, the higher the spatial resolution you get. But you can't fire a very large antenna in space. We've done it a couple of times, but it's difficult. So what you actually do is you synthesize from the individual recordings the signal as if it was collected through a larger aperture. So that's what synthetic aperture radar means. This satellite is flying relatively low among the Sentinels at 690 something kilometers. It's a relatively large satellite at a couple of tons again because of this high energy demand, and it's on a quasi-polar sun-synchronous orbit, which just means that it's passing from north to south, and it flies over the same region of the Earth at the same, pretty much every region of the Earth at the same local time, around 10 o'clock in the morning. This is a tricky thing to do because the orbit has to have a bit of an ellipse shape and always circle the Earth around in approximately the same speed as the Earth is rotating. But it's a very nice thing because then you get really consistent data. It works in the C-band, which is 5 gigahertz, or what's interesting for us, 5 gigahertz means approximately 5 centimeters of wavelength. And this is something to keep in mind, right? 5 centimeters. This is the size of structures that Sentinel-1 is going to interact with. We're going to see this in the imagery. If something has a a periodic or a regular structure of about 5 centimeters, you're going to get the strong Sentinel-1 signal. If the structure is smaller, like snowflakes or raindrops, you're not getting the signal. If it's much larger, like a flat surface, you're not getting a signal either. It actually has several modes. It's emitting signals at different swath widths, and this is going to change the coverage and the spatial resolution. So we have the interferometric wide swath mode, which is the typical operation over land. This gives us 5 days revisit time and a physical resolution of 5 by 20 meters for each pixel. This is then resampled to 10 by 10 meters. And at the moment, since Sentinel-1, I think it's 1A, is down, we're not covering all the globe with it. So large areas of mostly uninhabited places, forests, deserts on the globe are not surveyed with Sentinel-1. We hope that when Sentinel-1C goes into orbit, then this is going to change and we are going to get global coverage again. We also have strip map mode, which gives us a much narrower swath and a much higher resolution. This is only used at the moment for small islands in the ocean, and especially in connections with disasters. Amazingly beautiful pictures, but no global coverage. And then we have the extra wide swath mode, which is happening over the oceans with 20 by 40 meter resolution and the 400 kilometer swath, so a much higher revisit time. What we use Sentinel-1 for is ground motion detection. Actually, this radar processing enables very, very accurate calculation of change in strongly reflecting targets. So if you have a tarmac surface or if you have a physical corner reflector, you can detect the movement of that at the scale of millimeters. This is not something we can do directly in Copernicus data space ecosystem, unfortunately. It must be fun. The main reason why we like to work with Sentinel-1 is that it sees through clouds. So wherever optical satellites don't really give you a meaningful signal because it's cloudy, Sentinel-1 still sees through. And this often makes it the first point of response for disasters. If you have a flood, if you have a hurricane, the first images you are going to get of the situation are very, very often Sentinel-1 images. So we use them for flood detection. It's also sensitive to wave conditions and to ice. So we can use it for oil spill monitoring, for monitoring shipping, finding ships in the dark. And I'm going to tell you a story about this in a second. Vegetation monitoring to a certain extent, and complementing large-scale soil moisture, downscaling of soil moisture studies. So it's quite a versatile satellite, actually. What we see here is the floods around Oxford in 2021, early 2021. This is actually a composite. The background, the black and white image is from Sentinel-2. It's a mosaic we used as a point of reference to see which areas are flooded. And the blue ones are all the water surfaces from Sentinel-1. You can see that it's slightly sort of grainy and patchy, but it's been collected through cloud cover. So again, this was the first image after the flood happened, and this gave the emergency responders a really, really detailed map of the affected area and the damage. We are seeing these images more and more, unfortunately, with climate change, but Sentinel-1 definitely plays a very important role here. And then this second little example image is about ship monitoring. Can you spot the ship? Actually, we don't have a pointer, do we? Or a stick?
I don't have, but
Never mind. You see this inlet over there, and you see 3 little spots. 2 of them are yellow, and one of them is red. Right? Those little spots are ships. This is actually the icebreaker Polar Stem. There was a very large polar research expedition conducted in early 2020. And if you remember that time, that was when COVID started. So the ship went up to the high north. It froze into the ice in a planned way, just like the Fram back hundreds of years ago. The plan was to resupply it by helicopter and to change the scientific staff every 2 months. And then COVID happened. And so those guys were sticking up there for more than half a year with nobody exchanging the staff. Nobody could touch them. And then after a while, in the next summer, I think this is actually May or June, they managed to break free of the ice, and the pandemic situation improved sufficiently to allow a resupply of the ship. So they sailed down to Svalbard, Spitsbergen, and they went into this bay, and they met another icebreaker ship called Sonne, which gave them fresh food and took off the tired scientists and replaced them. And so this image was taken through complete cloud cover again. That's where you see the ships. And you may know that now every ship on the high seas is required to carry a transponder, an AIS. So the position of ships has to be public. And this is the way to check the ships that are not carrying an AIS. So we found out things like 75% of global fishing is unreported because we could see the ships. We found out things like, again, Russia transferring oil illegally and breaking the sanctions in collaboration with other countries by 2 oil ships meeting on the high seas and pumping oil from one to the other. So tracking ships is a major thing, actually. And Sentinel-1 is helping us a great deal in doing this in all conditions. Well, so much about Sentinel-1 for now. Our favorite workhorse is Sentinel-2. This is a multispectral imager flying a bit higher, 786 kilometers altitude. It's also a lot lighter. It's about half the size of Sentinel-1, since it doesn't have to generate all that energy. It has one single sensor, the multispectral imager, and this is collecting data at 13 spectral bands with a swath width of nearly 300 kilometers. So at the equator, it passes every 5 days. And then as you go further north and south, of course, the overlaps are going to increase and the repeat time gets shorter. This is optimized for vegetation mapping. So it does have true color optical bands, but it also has a broad near-infrared range band at 10-meter resolution. And we will see how the infrared region is very important for vegetation. It has 20-meter resolution for red edge and shortwave infrared bands. Shortwave infrared is sensitive to temperature to a certain level. And red edge is the point of the optical curve where the condition of the health of vegetation is really easy to observe. So at the red edge, it has 3 narrow bands, which allow you to estimate the position of the optical spectral curve in a really detailed way. And it has some bands specified for atmospheric correction. So finding clouds, estimating the structure of the atmosphere in order to get really, really high quality images. The main application of Sentinel-2, the main civilian application, is agriculture monitoring. So now with the EU Common Agricultural Policy, every country is required to monitor every single parcel, and that's done mainly by Sentinel-2, reporting crops, finding whether the farmer complies to regulations in terms of erosion reduction, catch crops, mowing. These things are regularly done at the day-to-day level with Sentinel-2. It's a massive amount of data. Hungary has 1 million parcels, and every Sentinel overpass is processed there. Forest monitoring, generic land cover mapping. We know that land cover is playing a very, very important role in climate change. Actually, the temperature that you feel or the microclimate that you experience is changing more because of the change in land cover than it is because of the change in global warming. So that's a big deal. City monitoring, actually, now identifying areas with low green cover or areas with rapid urban change are very important. Fire monitoring is becoming an important application, again, unfortunately, more and more frequently. And often humanitarian monitoring, checking things like refugee camps or conflict areas. Sometimes even actual open source intelligence investigations into what happened in a specific place. Since the global coverage is there and the resolution is there, it's often possible to follow up on events that are happening on the ground. Often, again, Sentinel-2 is the only source of information. This is just a nice little visualization of agricultural growth stage. We are going to use this script in a bit later. What happens here is we are taking a time series of 3 months of Sentinel-2 images. We are estimating the peak NDVI, so the point where the vegetation was the greenest. And then we are assigning this to the RGB channels. So if the vegetation was the greenest in May, then the parcel is going to be red. If it was the greenest in June, then it's going to be green. And if it was the greenest in July, then it's going to be blue, and all combinations of these. So the white areas are places where the vegetation doesn't change much, grasslands or forests. The black ones are places that have no vegetation at all, bare soil. And then already this very simple visualization is giving you an impression of crop conditions across this site. It's a really easy to use thing. This is another application of Sentinel-2. It's used heavily in water monitoring, water quality monitoring. The spectral properties are not really optimized for water. It's not ideal. This is what Sentinel-3 is going to be for, but you can see a lot of structure. So again, this is a sediment plume. We are in the French town of Nice, and after a rainstorm in the mountains, a lot of water is coming down and bringing a lot of sediment, and you can see how it's mixing with the ocean. This little reddish pattern here is probably an algae slick. So we also see that to a certain extent. It's not very easy to separate sediment from chlorophyll in Sentinel-2, but it's very good in giving a map-like qualitative overview and helping with interpreting the patterns that you see in your samples. Sentinel-3, it's also a multispectral imager. It's actually designed for ocean color and water quality monitoring. So it's based heavily on the legacy of MERIS. Actually, most of the algorithms that worked with MERIS also work with Sentinel-3. And already MODIS has contributed massively to our understanding of the global carbon cycle, the role of oceans in absorbing carbon, mapping global chlorophyll patterns, understanding El Nino, things like this. So this is sort of the legacy that Sentinel-3 is following on. We have 2 Sentinel-3 satellites, and we have daily reset across the whole globe, including the oceans. So this is, again, the satellite that's taking an image everywhere. It has a multispectral imager with 21 spectral bands, so really, really fine spectral resolution. Again, optimized for water quality, but of course working for many different other applications. It has a spatial resolution of 300 meters. So, well, still relatively detailed compared to MODIS. It's not trivial to create true color image, actually, from Sentinel-3. That's not what it's used for. It doesn't have the typical setup of optical bands in directly in RGB, but it's really useful for chlorophyll, for water monitoring. It also has another sensor, the sea and land surface temperature radiometer. This is giving us 1 kilometer resolution thermal data, again, from all over the globe. Thermal imagery is heavily influenced by clouds. That's actually one of the reasons why we are collecting it, because it helps with cloud masking. The top of clouds is always cold. So in cloudy areas, it's not that useful, but wherever we are free of cloud cover, especially in heat waves across Europe, and we're going to see that script again, the SLSTR is really nice as well. Oh, thank you. It also has a synthetic aperture radar altimeter for measuring the height of the ocean. I don't know how much you know about ocean geodesy, but currents often stand out from their neighborhood a little bit, in a couple of centimeters or decimeters of height. And so if you're able to understand the current profile through these heights and the chlorophyll or sediment pattern, then you have a much more detailed understanding of ocean physics. And it also has a microwave radiometer. So this is actually an ocean satellite, but we use it also for meteorology, for sea ice thickness mapping, wildfires, sea level, and this global regular coverage is really quite nice. Might as well even plug this in, right?
If you want to use it for step,
okay, I'll do it in the break, but I can use the pointer, right?
Yeah, on this tag. Yeah.
Here we go. So this is an image from Sentinel-3. I don't know how much you see from the back. This is a very, very characteristic cloud pattern called von Karman vortices. We have a wind coming from over here, and then we have the turbulence patterns in this regular shape from right to left and left to right in the wake, in the lee of this island. This is Guadalupe, close to Baja California. And the width of this image is something like 500 kilometers. So this is the scale of patterns that we observed with Sentinel-3. This is another example. This is Sentinel-3 water quality product. So actually, it's already a downstream process thing. It's processed to micrograms per liter chlorophyll. We are along the coast of South Africa and Namibia. So this is the Benguela current, a very important current supporting a large fishery. We have this cold water upwelling, which is creating chlorophyll patterns, and these can be followed across the ocean, again, every day when there are no clouds. So this is a useful thing to have. And then actually, have you ever heard about Sentinel-4? Nope, it's not there yet. It's not there yet. Sentinel-4 is an atmospheric high-resolution hyperspectral instrument, so it's going to measure atmospheric pollutants. It will be placed on one of the Meteosat third-generation meteorological satellites, and it's going to be a geostationary satellite. So this satellite is going to orbit always above Europe and North Africa, and that enables it to have very high temporal resolution within a couple of minutes to check weather patterns and to check atmospheric pollutants. I think this is going to be super important for greenhouse gas monitoring and public health. The page of ESA says that this satellite is going to be launched in 2022, which apparently didn't happen. At the moment, I've searched, and the estimated launch date is going to be second quarter of 2025. So if all goes well, next year we're going to have Sentinel-4 as well. Probably also inside Copernicus data space ecosystem, I hope. And then we have Sentinel-5. It's actually called Sentinel-5P at the moment. Sentinel-5 is also planned to be launched on a meteorological satellite, where we're waiting for the satellite to be manufactured. But in order to have the temporal continuity, a precursor was launched on a specific ESA-driven or Copernicus satellite. This is Sentinel 5P, which is an atmospheric hyperspectral imaging mission. Again, we have very high spectral resolution. We are aiming not at the ground, but at the atmosphere. And this gives us high resolution or high temporal resolution mapping of atmospheric pollutants. Sentinel 5P also has daily visit times, which is nice because it helps with cloud masking for other satellites as well. And the sensor is called TropalMeet. This is a multispectral imager working at a 2,800 kilometer swath width. So compared again to Sentinel-2, which has a 300 kilometer swath width, this is nearly 10 times the area. But of course, this goes at the cost of resolution. So the resolution is 7 by 3.5 kilometers. So it's big. You see cities, you see urban areas. If a single point source pollution is showing up on a Sentinel's 5P image, then we are in big trouble. But sometimes it happens. So this is mapping nitrogen dioxide, methane, carbon monoxide, formaldehyde, ozone, sodium dioxide, these atmospheric pollutants which are important for climate monitoring and also for public health. This is an example of Southwestern Europe. It's actually a monthly mosaic. So this is the monthly mean of nitrogen dioxide pollution. And you can see a couple of interesting areas. This is Budapest, by the way. So we are somewhere over here. These are Carpathians. So good luck to those who are in the mountains. And this is the Po Valley, which is an industrial area with also very heavy traffic. And it's in the wind shadow of the Alps, which means that the wind is not really clearing out the pollution from here. This is the Ruhr area in southwestern Germany. This is the Netherlands, and somewhere over here we have Britain. Another image. Maybe this is going to be familiar to a couple of you. Do you remember these images? They were on mainstream news on BBC as well. The whole idea of COVID lockdowns improving air quality was proven by Sentinel 5P. And actually, it's a very, very controversial topic because some people say that more deaths have been prevented by reducing the air pollution than what we have had for COVID. So the whole public dispute of, yes, I've seen that in a scientific paper, a peer-reviewed scientific paper. It's probably related mainly to areas with very heavy air pollution, such as India. And of course, depending on how you calculate preventable deaths by air pollution. But the whole idea of recognizing the very, very heavy impact air pollution has on our lives was very largely a product of these images, these data sets. So good that we already had the sensor up there. We had it for climate monitoring, but it had a very strong implication also for public health. This is Sentinel-6, Michael Freilich. It was named after an important NASA oceanographer. This satellite is doing ocean monitoring. It doesn't collect data over land. And as far as I know, it's not an imaging sensor either. It's a radar altimeter, and it also has equipment for precise orbit determination. So measuring the sea surface at a very, very high accuracy, at the accuracy of a couple of millimeters, and also surveying the position of the satellite in order to estimate the sea surface thing. Actually, sea surface height mapping has a very long history going back to JSON and COPEX Poseidon, more than 3 or 4 decades now, and with a relatively consistent system of sensors. So we have quite a strong understanding of global sea level rise, where it's happening and what the speed is. And this is a product of satellite systems such as Sentinel-6. We're not going to work with Sentinel-6. It's not. It doesn't have data products which are in Copernicus data space ecosystem. All the ocean products actually are in what's called the Ocean Virtual Laboratory. Also a very nice interface if you want to play with it. But that's more of a fun thing if you're into land monitoring. Then we have Copernicus contributing missions. And again, I hear this a lot, that Sentinel satellites have too low resolution, or that they don't cover a specific part, such as topography monitoring. In the Copernicus program, there's also a specific budget for buying satellite imagery off the market from high-resolution providers. And these data sets are then also processed to a consistent format, and they are served in what is called Copernicus contributing missions. So this includes Airbus data, Planet data, Pleiad data. Most of it is used for high-resolution city mapping and monitoring. And these missions or these data sets are also accessible for Copernicus data space ecosystem. Some of them are commercial radar products, which are used for ice monitoring. Again, ice monitoring is a very big deal for shipping in the Baltic Sea and around Northern Europe, because you save a heck of a lot of money if you go through the right places where the ice is thinner. And of course, there's also a security aspect to it. So Copernicus contributing missions also include snow and ice products over the Alps and over the seas relevant for Europe. This is an example of a Copernicus contributing mission dataset. This is a museum called Aeroscopia in Toulouse. The image has a resolution of, I think, somewhere around 2 meters. And this guy here is the Concorde. So this is the level of detail that you get with Copernicus contributing missions. And then we move over to Copernicus services. So again, the whole idea is to create data that can be readily used by non-specialists, people who are not into Earth observation. We want to create standard products with verified algorithms where people can actually base decisions on. I like to tease Hungarians with the issue that there's no Hungarian word for evidence-based policy. How do you say evidence-based policy in Hungarian? Anyway, this was the concept of the Copernicus services. We are trying to support policy decisions based on evidence. We are making the information free for everyone to make it accessible by processing environmental data and Earth observation data and creating a system of interoperable, searchable, free and open data products. And again, if we're talking about policy, Copernicus is on one hand enabling governments to have more control over what people are doing. This is what CAP monitoring is about. But it's also enabling people to have more control over what governments are doing, because the data is out there in the open. It's very difficult to hide something. It's very easy to collect quantitative information, and people can be held accountable for international commitments about pollution or biodiversity. It's making it easier for NGOs or local people to actually make their voice heard based on evidence. So one of these services is the Copernicus Atmospheric Monitoring Service. This is driven by the European Center for Medium-Term Weather Forecasting. So actually, they are the subcontractor who are operating this service. They are publishing maps of atmospheric quality, atmospheric composition. They are monitoring the ozone layer and ultraviolet radiation over Europe. They are looking at emissions, solar radiation, also for solar energy, and modeling the climate and making forecasts. So these data sets are used by weather sites and by public health agencies across the world. And Copernicus Atmospheric Monitoring Service has its own website and its own data store. We hope that at some point this is going to be integrated into Copernicus data space ecosystem, but at the moment it's a separate data set. Then we have the Copernicus Marine Monitoring Service, which is implemented by Mercator Ocean. They have their own data store. They have their own data products related to water quality, also including, inland waters are done by Copernicus Land. Marine safety, looking at ship traffic, looking at fisheries, trying to enable sustainable use of ocean resources through quantitative data. Again, the main users are mostly governments, sometimes shipping companies or large fisheries, but mostly governments are using the data from the Copernicus Marine Monitoring Service. And then we have our friends at Copernicus Land Monitoring Service. This is mainly implemented by the European Environmental Agency, and they are very closely collaborating with Copernicus Data Space Ecosystem and also specifically with Synergize. The main output here is land cover and land use mapping. So if Korean land cover rings a bell, this is one of the products of the Copernicus Land Monitoring Service, but now it's being revamped into a product which has much more temporal detail. It's going to be in a much more operational way. There are some thematic biodiversity or urban hotspots, which are also mapped in high detail. Ground motion detection is part of Copernicus Land Monitoring Service. And in general, vegetation and crop monitoring is an important product. So these guys are actually working hard on integrating their data in Copernicus Data Space Ecosystem. Actually, the land cover maps are already there as a data product, and you are going to explore them. Copernicus Climate Change Services, again, provided by the European Center for Medium-Range Weather Forecasts. These are the guys who are producing the European State of the Climate Report. So again, they are one of the very, very strong scientific bodies who are trying to influence policy by giving strong data products. There's also a really nice Copernicus Interactive Climate Atlas, which has its own interactive map surface worth exploring. They are, of course, providing climate indices, but also climate projections, seasonal forecasts. So this is a really nice set of services, and it's also complemented with a network of institute observations of weather and climate. And then we have the Copernicus Security Service. They are providing the satellite data, which is serving the common security policy of the EU. So this includes border surveillance, maritime surveillance, also support to EU external, mainly military actions. The key partner here, they are not the ones doing the whole thing, but most of the stuff is done by the European Union Satellite Center in Spain. And they are trying to provide situational awareness and data for crisis prevention. If there is some sort of military operation or intervention, or if there is a border crisis, then they are the ones who are trying to exploit Sentinel data and provide information. And then we have the Copernicus Emergency Management Service. So these people are operating a rapid response service, trying to publish data as fast as possible if there is a disaster somewhere. There is a European flood awareness system with flood forecasts and flood maps. Actually, it's worth taking a look at this if you live close to a river. Then there's a European forest fire information system, also with very nice interactive maps and very clear predictions. The European Drought Observatory. There's a global food awareness system, which they're operating for the sake of global food security and also the connection to crisis or conflict. There's a global wildfire information system. So, and the Global Drought Observatory, which is different than the European one. So this is part of sort of the European common response to disasters within or outside Europe. So put it together, this is what the Copernicus program is about. It's a whole vertical, really, from working with the space systems to downlinking and sharing the data to building services on top of them for citizens. Actually, there has been quite a lot of scrutiny into the usefulness of the Copernicus program because it's a very big investment. So, of course, the Commission wants to know whether it was worth it. And they contracted the European Association of Remote Sensing Companies to create a really large-scale quantitative report, which is called the Sentinel Benefit Study, also worth reading. And one of the conclusions they found was that Sentinel data are contributing, or the Copernicus program is contributing to greater transparency of public policy. And this is improving the trust of citizens in public authorities across Europe. And I think that's a really nice thing. And so I'm super positive about the way the Copernicus program is working up, and I really hope that it's going to continue in the future. Thank you for the first unit. Questions. Give me questions. Sure. Also, we can, online people, don't hesitate to drop your questions in the chat or the Q&A. Hopefully the Q&A. Yes, please. Okay, no questions so far from online people. Yes?
I would like to ask one thing, that you were talking a lot about the public access or open access to the data. But what if somebody wants to make an enterprise using this data and commercializing value-added services? Is there any way of getting guarantee that the data will be always there, and does the user have to pay for it?
Copernicus, and specifically Copernicus Data Space Ecosystem, has what it's called a service level agreement. Normally, if you are buying Earth observation data from an industry company and you make a long-term agreement to sustain the data, then there is a legal contract called the service level agreement, which includes things like the estimated uptime and downtime of the system. So like they commit to having 95% uptime, the resolution, the quality of the data. And then you sign this and some money is exchanged. The Copernicus program also has a service level agreement. So now there is a legal document actually outlining the commitment to the quality and the services that we are promising. And if we are not living up to that service level agreement, then any company can sue us or the Commission. So that's actually a big deal that we have committed to this. The data are completely free for any kind of exploitation. I'm not sure about export to some countries influenced by conflict, such as Russia. And Copernicus contributing missions can only be used for research and nonprofit applications. So that's something, these high resolution data sets where you don't have the license to actually build on them in a commercial way. For that, you would have to have a separate contract with ESA. But everything else is completely open, completely public for any kind of application. Actually, Australians are super happy about this. So one of the largest users of Sentinel data is Australia. They are powering a lot of their monitoring, drought monitoring, climate change monitoring, agriculture with Sentinel data. They're kicking it for free and they're using it. But I think that this is in the public interest. More questions? Yes, please.
Also on this, and if you have a financed research project, can you use the data? The project is financed. It's a
The Copernicus contributing missions data?
yes.
I'm not sure. You would have to check.
Because you said that it's free for research, but if you are doing the research through a financed project,
It is the research.
I would expect it to be free, but I don't know the exact details of the license agreement.
Someone asked the question. There are plenty of.
Yeah, let me see. The relationship between the Copernicus programs and EUDR requirements. Do you know what EUDR is? It's the European Union deforestation regulation. EU is making a commitment to having absolutely all production deforestation free. So if you want to sell something in the EU, whether you are producing it within or outside the EU, you will have to be able to prove the whole supply chain of that product and to prove that it hasn't caused any deforestation since the benchmark of 2020. So it's a very, very ambitious target, actually. And of course, it's based on Copernicus. Yes, I think the plan is to create some sort of base map for this benchmark year of 2020. And then that should allow operationally following up the regulations of the UDR using satellite data. I think it's going to operate quite in the way as cap monitoring does, where again, public bodies are overseeing production on parcels with satellite maps. Recently, EUDR has been postponed by a year, and the message was that this is because of data processing problems. And I was worried because I thought this is because of Earth observation problems, but no, it turns out I've spoken recently to somebody who works for a large paper company in one of the Nordic countries. They say that the problem is tracking the individual items that you are producing. So if you chop down a tree, then the branches are going to a separate, market, and the trunk is going to another one. And creating identifiers for all these products is going to be a big deal for some sort of IT network. But the EU is still committed to doing this. So I really think that Copernicus data is going to play a very important role. Another question about land use in agricultural producing countries. I would appreciate if you could just type in some more details to this question, Bernardo. We are producing land use maps across the globe now, and we are really, really trying to exploit Sentinel data to actually have globally, regularly updated land cover maps. This is a follow-on project to Corine, which is under implementation right now with the European Commission. No, with the European Environmental Agency. More questions. Somebody asked the question in the Q&A. Oh, which CDSC data is not available for commercial use? It's Copernicus contributing missions data. So Sentinel data is available for commercial use, and these Copernicus contributing missions data sets are not. Those have a separate license. You will see them as CCMs, Copernicus contributing missions in the documentation. We'll take a look at that in the hands-on.
Can you give an example?
Yes, the high resolution urban atlas mosaics, or the again high resolution images of sub-Saharan Africa collected within the CCM project. These are not free for commercial use. Also, there's a 10-meter Copernicus elevation model of Europe, and that's not available for commercial use either. That's also a CCM data set. We don't have it in the browser yet, but it's already available through Stack.
But I may give you an example. For example, some companies like they're working with the GIS and special image satellites. They use the data in order to make it to trigger their project for some countries because they need to money, especially in the developing countries.
Yes,
Is that legal?
I think so. I mean, if you're talking about Sentinel data, I would expect it to be legal. Yes. We have a question from Luck. Yes.
Yeah, so which is the sensor or equipment used to do these high resolution images?
It's several different sensors. So actually, Then let me go back. I don't know how much you see on this slide. Here we are. Yeah. So it says Airbus, Pleiad, Planet, ComSat. So it's actually a network of various commercial satellites, which the ESA commissions individually to make images of a specific area and phase for it, and then the data is published under the Copernicus Contributing Missions license. I think it's also a very nice entry point to start working with commercial data, because maybe there's no data over your area, but maybe you can take a look at the CCNs and then you can decide whether it's worth pursuing a commercial contract.
What is the highest resolution of 1 meter of inner?
I think it's around 1.5 or 2 meter Pleiad.
Pleiad is 0.5. What about?
That's Pleiad now, isn't it? Pleiad now is 0.3. It could be 0.5 up at punch sharp and
Yeah, it is.
yes.
What is your opinion about the use of the drones behind these images?
Oh, scaling up and scaling down. So that's always an issue. You know, we have a 10-meter satellite pixel and we have that data across Bigloma. And then we are measuring some parameter like soil moisture for I don't know, species richness at one single point. And then at the easiest level, you are actually taking that point and you are extrapolating it to the 10-meter satellite image pixel. And you are already working a lot better than if you wouldn't have the satellite image pixel, because, you know, then you would be extrapolating between this sample and the other sample 5 kilometers away. But if you want to have very high accuracy and very good models trained, then you need to close the data. And very often drones or airborne images or airborne LiDAR come handy, because then you can go from 10 meters to 1 meter and from 1 meter to 5 centimeters. And you won't have the data everywhere, but this will allow you to sort of scale up. And that's not just about making more accurate predictions, because maybe your predictions are not going to be that much more accurate, but understanding the error budget, understanding the uncertainty of the prediction you make based on Sentinel, because you've been through the scales one by one from your sample, through your drones, through your airborne data. So that's a really nice way actually to apply drones. I think drones have a big future in all this, in agriculture or environmental studies. And again, drones are different. Some drones are small and you can fly them every day, and some drones are nearly as big as an aircraft, still a bit cheaper to fly. So I think that it's really about the scaling. More questions? Yes. So the land use, the question of Bernardo related to EUDR also includes the relevance of land use within EUDR. So it's not just deforestation, but also the land use itself. Yes, as far as I know, Copernicus data is going to be heavily used for land use mapping also in the context of EUDR globally. If I would be creating an urban Earth observation startup, then I would probably focus on EUDR.